Welcome, everyone. My name is Peter. I'm with the program committee. I have the pleasure of introducing Murray Steele today, engineering manager by day, co-organizer of the London Ruby user group by night. Murray cares about encouraging a sense of curiosity and play while programming. Please give him a warm welcome.
Thank you. Hello, I'm Murray. Thanks for coming to my talk. I'm an engineering manager at Clio. We're based in the UK, but our customers are in the US. We're empowering people to build a life beyond a paycheck. And we do that with an AI assistant that understands your banking information in order to give you personalized and relevant advice on your personal finances. And for a fee, access to a range of services to actively help you improve your situation. But I'm not talking about anything related to that today. But if it sounds interesting, we are hiring and we can help with visas and relocation, so come and find me later. I have this face. You'll find me. What I am here to talk to you about is files and data, and let's just get started. So here's a screenshot of a fairly standard downloads folder. All these different types of files, pictures, movies, documents, audio. The file names include the title of the file, and after the dot, what's known as a file extension that tells you what kind of file it is. In a modern graphical operating system, you don't have to parse that extension yourself. Your OS does it and gives you a handy icon to tell you what the file is, and maybe even a hint as to what application will be used to open the file if you double-click it. Indeed, if you rename the file to change the extension, this will very likely change the icon and the application that will open it. Your OS might even warn you about that. When I first started using computers, I thought this was all that was involved. Rename the file and you'll be able to use it. Of course, it's not. When I tried renaming a file from .doc to .txt, I didn't have Microsoft Word at the time. I couldn't open the file to read it in Notepad. It was just a stream of nonsense. I did try the example in the screenshot. I hoped that if I renamed a PDF to a WAV, it would magically be able to read all the words in the PDF out to me. Obviously, it didn't. It just gave me an error. So there's more to it than just the file extension. What's going on? On Unix systems, there's a command called file that if you give it a file, it will do its best to tell you what that file actually is. So interestingly, one of the things it does is open the file and take a look at some of it to have a guess. It doesn't just take the name of the file on blind faith and say that, yeah, this is a text file, if it really is a zip file. So going back to my youthful attempts to open files without the relevant, usually expensive software, this explains why it didn't work. You can call your file whatever you want, and the OS may use that for some hints as to what application will open the file. But it's what's actually inside the file that really matters. Renaming a doc to a TXT won't let you get at the words inside it. Renaming a PDF to a WAV won't let you listen to the contents of that PDF file. I'm wiser now, and I understand my youthful folly. But at some point in my early terminally online life, I came across a website that described the data structure for WAV files. WAV files, if you don't know, are simple, uncompressed sound files storing like a digital representation of a recording of an actual sound. The ones and zeros of the data are the numerical values that represent the sound wave, hence the name. And they are very simple. They're made up of a header part and a data part. The data part is just that. It's raw bytes that represent the digital representation of the sound wave. Just a stream of numbers, really. There's lots of different ways to interpret those numbers, and that's what the header part does. It tells us how to interpret the data. The header part is split in two. The first part tells the world, hi, I'm a WAV file, and I'm this long. It's very short, and is there basically to tell other software, if you don't know what a WAV file is, you can stop now. That's definitely the voice of a WAV file. The second part tells the audio software how to interpret the data that follows. Things like how many channels, is it mono or stereo? How many samples there are per second for the sound, how many bits there are per sample. How detailed this data is, more channels, more samples per second, more bits per sample, means the sound is more accurate, but you need much more data to represent the same length of sound. Okay, so we can't rename a file from taxreturn.pdf to taxreturn.wav and expect to be able to listen to it. But given how simple the WAV file format is, we could take a PDF file and put a WAV file header on top of it, and then we can listen to it. How? Well, a WAV file is header and the data bit's easy. We just take the entire contents of the PDF and smoosh it onto the bottom of our WAV file. We can then calculate what we need for the header just by looking at the size of our source file. And making some choices about the sample rate and bits per sample, we can calculate the second half of the header. So here's some Ruby code that constructs the header. Let's go through it. This first stanza builds the whole of the identifier and length part of the header. E.g., I'm a WAV file, and I'm this big, including the size of the header. That's the magic 36. The second stanza constructs the first part of the data header. Our arbitrary choices here are the instance variables, like what the sample rate is and bits per sample will be. And we combine those with some calculations on the file size to explain how to interpret our data. There's some more magic numbers in here too, but trust me, while they're important, they're also boring. The third stanza constructs the final part of the data interpretation, which again uses the file size to explain how much data there is. As we saw, after this header, we just have the raw bytes that make up the actual sound data. So what's missing from this code snippet is how you actually copy the data around between files, and I'm sure you could all just imagine that, so I'm not going to show it. All that's really interesting about this code, I think, is the pack method. I don't know about you, but in my day-to-day coding life, I'd never encountered it before. So this is what pack does. Called on an array of numbers and passed a format string, pack will convert those integers into bytes. Now, why is that interesting? Aren't numbers bytes anyway? Well, it turns out there's lots of different ways to represent a number in bytes, and pack lets you control that. So you can say, represent this number as a 4-byte number, or represent it as a 2-byte big endian number, or a 2-byte signed integer. You don't need to know what those words mean, but trust me, it's important when you're thinking about bytes. What a WAV file cares about is that some of the header is a 4-byte number, and some of it is a 2-byte number. And that's what these pack statements are doing. It's a big V for a 4-byte big endian, and it's a little v for a 2-byte big endian. And that's basically all there is to it. As an aside, that code had a lot of magic numbers in it. At work, we've got a custom RubyConf rule published as a gem that shouts at us if we've had any magic numbers in our code and tells, go and define a named constant for it. But this code is personal and for fun, so best practices be damned, right? That said, coming back to this code, I did wonder what that 16 was. Is the 16 special because we're talking about bytes and it's a multiple of 8? Or is it something about the WAV file format? I don't remember. I'm sorry. If I'd given it a name, maybe I would. So, like, best practices are good, actually? Anyway, we've seen all that code, so why don't we try it out? So first we will require my library. It's called Stegosaurus because I kind of thought this code might be, have I spelled Stegosaurus properly? Yes. I thought this code might be like a steganography tool, hiding data within other data. And also, dinosaurs are cool. So we've got a library called Stegosaurus. We can grab an object from it. It's a wave object because we're building wave files. We can make a wave file from a file. We're going to need a file. I've got a README in the repo. It's about 1,000 bytes. That should give us something interesting, right? So we will do that. Oh, I need to capture the... And then I've got a convenient little helper method to let me open this file. Okay, it's very short. As I said, the wave file format really needs a lot of data to get you to hear something. So we're going to need a bigger file. There are probably bigger files lying around, but the big file I know that I definitely have is the Ruby interpreter itself. So Ruby comes with this nice little module called RubyConf, which has lots of details about how Ruby was built. But the important method that I care about is rubyconfig.ruby, which gives you the path to the currently running Ruby interpreter. So if we stick that into our, oh my goodness, never do live demos. If we stick that in there, we'll be able to hear the Ruby interpreter itself as a WAV file. I hope you're ready for this. What? Oh. Never do live demos. Okay, I hope you're ready for this. Yeah, so it's basically unlistenable white noise, right? Fair. What did we expect? But what is kind of interesting and is, as we skip through it, that's probably enough. There's some structure there, like different parts of the file sound different. If you're old and dusty like me, you can thank me later for the nostalgia trip you just had about loading software from tapes or dialing into the internet over a telephone. Cool, so that was kind of interesting. You don't want to listen to it, but it's interesting. And there was some structure there. So we explored the WAV file a bit, and there was some structure. I think that's interesting. I'm not going to listen to all that white noise, though, and get attuned to the differences. So what if there's another way to explore the structure of the file? A visual way, maybe? If we can listen to our files as WAVs, is there a similar shaped format to let us look at them, too? Yes, there is. There's the BMP image format, bitmaps. It's got a header and then pixel data, so we should be able to do basically the same as we did with WAV files. Calculate the header and write out our source file as the image. If you look at it in a bit more detail, yeah, header and data. The data, as you might expect, is the pixel data. It's color values for each pixel in the image. The header can be split into 3 parts. There's an opening segment with the BMP identifier and the length of the file. There's a second segment that includes information about how to interpret the pixels, so like the width and height, the color depth, DPI resolution if you want to print these bitmaps out to like inches. And there's a final segment that describes the colors used in the image. Bitmap is an indexed color, so the pixels are not red, green, blue values, they're a number into the color table. It's nothing we've not done before with WAV files, except the pixel data part is a little more complex. We can't just throw all the data at the end of the header and expect it to work. There's 3 problems that we have to solve. The first one is color depth. How many colors does the image have? One of the arbitrary choices we make is to choose a color depth, and that has an impact on the amount of data we need. If we want a monochrome image, we choose 1-bit color depth, and each byte of our file is equal to 8 whole pixels. So a 25-byte file becomes a 200 pixel image. If we want more color, 256 to be exact, shout out to VGA, we can choose 8-bit color, so 1 byte, 1 pixel, 25-byte file, 25-pixel image. What if we want even more colors? We could choose 24-bit color, true color, 16 million colors. Like, your eyes will not be able to cope with that. Our 25-byte file is now a glorious 8 1/3 pixels. If we don't have a complete pixel, a bitmap renderer is just not going to show the image. So what do we do? Pretty easy. Unlike any other programming problem, it is null to the rescue. So we just add null bytes to the end of the file, at the end of the data. We can work out how many whole pixels the data would create and how many padding bytes we need to complete that last pixel. Just a function of the file size and the color depth. Problem solved. The second problem is one of rectangles, width and height. Images have to be rectangles, so we need to arrange our pixels into rectangles. Our padding example is really simple. We've got a 25-byte file, which we pad to 9 pixels. 9 pixels is a lovely 3x3 square. Easy. It's not always that simple. What if it's a 28-byte file? That gives us 10 pixels. Yes, you can rearrange that into a 5x2 rectangle, but factoring huge file sizes to find convenient rectangles that will also be reasonable to look at on a screen might be painful. We don't want wide and short or tall and skinny images. Simplest thing is just to work with squares. So it is null to the rescue again, hurrah. We have a simple algorithm for calculating the smallest square that contain all our pixels. We get the number of pixels, 10. We take the square root, 3 point something. We round that up, 4. We square it, 16. We subtract the number of pixels that you have, 16 minus 10, 6. So we have to stick 6 padding pixels onto the bottom of our image, and now we've got a square. It might be inefficient of extra bytes, but it is easy. This is like 2 or 3 methods of math. Our third problem is scan lines. Now, you could probably have anticipated the first two if you thought about the problem of like images, but scan lines are a quirk of the bitmap format. A scan line is a single row of pixels from our image, so our 28-byte file, 16-pixel images, is 4 by 4. So it has 4 scan lines containing 4 pixels each. For reasons, the bitmap spec says a scan line must be a multiple of 4 bytes. So this is fine for our 28-byte file because our rows are 4 pixels long. Each pixel is 3 bytes, and that adds up to 12, which is a multiple of 4. But if we go back to our 25-byte file, that's 9 pixels, a 3 by 3 square, which is 9 bytes per scan line, which is not a multiple of 4. So happily, it is also null to the rescue again, but we could rearrange the pixel data to make scan lines that are 4 bytes long, and then we pad the end of that file with null bytes, and this will work, valid scan lines. However, I kind of think we've wasted some of our data. If we look at it as bytes and pixels, you might see what I mean. When I rearranged the pixels into valid scan lines, some of those pixels aren't actually pixels. They're not visible. They're just there to appease the scan line rules. We can't see those pixels. If I overlay like a visible overlay onto this, you'll see what I mean. Those pixels at the end, those bytes at the end, are just there to appease the scanline rule. And it annoys me that 6 whole bytes of my data file are being stuck on at the end and I can't see them. So they're not showing me the structure of the file. So I give myself a self-imposed rule. I don't want to waste any source file bytes. It's my project and I can do what I want, even if it creates problems to solve, which I guess, like, that's why we're all here. Solve problems with programming, even if they're self-imposed and silly. I want to use as much data from my file as possible to make my image, so we're going to have to rethink. Instead of adding null bytes to the end, what if we add null bytes, instead of them adding them to the end of the file, what if we add them to the end of the scan lines? So, yeah, this gives me valid scan lines of 12 bytes, which is good. And we've not wasted any bytes, which is also good. So that's that problem solved. To recap quickly, here's all the padding we need for a single file. 24-bit color, 17-byte file. Arranged in groups of 3 bytes. That gives us 5 complete pixels and 2 bytes left over. So we add 1 null byte to complete the last pixel, giving us 6 pixels. That's not a square, annoyingly. So we add 3 pixels to get a 9-pixel square. These new pixels are made up of 3 null bytes each, so we're adding another 9 bytes. Another? Yeah. Our 9-pixel square image means we have 3 rows of 3 pixels each. I've read that already. No, I haven't. Our 9-pixel square image means we have 3 rows of 3 pixels each, which is 9 bytes, so we add 3 bytes per line. To get our multiple of 4, this completes our scan lines. Total padding, 19 bytes. Yes, that's more than the original source file, which is inefficient, but like this is an extreme example because of the small input file. You probably don't have any 17 bytes files on your computer these days. They're all huge, right? What's interesting about this is we can see that pixel and rectangle padding just go to the end of the source data, but the line padding has to go inside the source data at the end of each line. So I said the code for WAV, for writing the source data, was uninteresting, but it's not for bitmap, so here's a little snippet. We pull pixels from the file based on how wide the image will be in pixels. We pull bytes from the file based on how wide it will be in pixels, and then we write them to the target file. And then we add the scan line padding bytes, and then we repeat this until we've exhausted the file. What's most interesting here is our top line where we construct the scanline padding. Our friend pack is back, but we're packing from an empty array. What's going on there? Well, it turns out if you want null bytes, you can create an array of the right number of zeros and pack with the appropriate command string, depending on how many bytes you want that zero to take up. Or you can just use an X. And if you use an X with a number followed after it, it'll generate that many null bytes. And it doesn't use up any of the numbers in your array. Here, we only want null bytes, so we can pack on an empty array. We're getting something from nothing. That's neat. As another aside, there's a whole lot more that pack can do. But spoilers, this was our last outing in this talk. To learn more, I recommend this post on Jan Lellis's Idiosyncratic Ruby blog. The whole blog is great, though. Thanks, Jan. I don't think you're in the room, but thank you. You should go and read that. So there's a lot more code in this one, but mostly it's uninteresting. As you can imagine, the code for dealing with all the other padding we calculated is a load of maths. You can probably imagine it. There's also code to generate a color table as 4-byte tuples. And although a critical reading of this code would be interesting, why have I used so many while loops? Why isn't bytes from more idiomatic and iterator-based? I don't know. We're not going to find out. So to save me from critical self-reflection on that code, let's have a demo and see what our data looks like. Cool. OK, so as before, we're going to grab an object. So we have a generator called bumps. We will do the same thing. We'll generate something from, no. Generate from the README again. OK, right, if this is working properly. That is tiny, but let's look inside. So there's our image, right? That's a bitmap generated from our README. The interesting thing you can see here is, like, at the top, the color sort of stops halfway through. Those are our null bytes. Bitmaps are upside down. That's absolutely wild. Thanks, bitmap people. But you don't get much from a short README file, do you? But one of the arbitrary choices we can make, bring the terminal to the front. One of the arbitrary choices we can make is the bit count, or the color depth. So why don't we generate a 1-bit version and that is maybe a bit more interesting. Let me just zoom in on it. So you can see there's a bit more structure here. You could probably learn to read this, just like that guy in the first Matrix movie. And then this could be how you operate with computers, right? That would be fun. Yeah, there's some structure there. That's interesting. OK. But I know what you want. You want to see Ruby as a bitmap. Come out with there. Yeah, you want to see Ruby as a bitmap, and I will make that happen. So what might Ruby, the bitmap, look like? An error. Oh, it literally is an error. Oh, no. Right, luckily, I think I have this file somewhere. I mean, live demos. You have to trust me that I did, in fact, generate this live before. Where's the, here we go. No, we don't want to zoom in on that. OK, so here's Ruby. This is Ruby, the bitmap. What can we learn from this? Well, bits of it are pink, which is cool because it's Ruby, so that's good. A surprising amount of it is this iridescent green, which, as we all know, there was some Perl influence on Ruby, as Matt shared this morning. So that's probably what that is. That's all the Perl stuff. And then there's this sort of scary dark bit in the top third. I guess that's maybe where the exceptions live. Yeah, I mean, OK, I can't interpret this, but we can look at this, and we can make up stories to describe what we don't know, just like our ancestors did. That's fun. That's fun, right? Cool. So we've looked at bitmaps and seen some things. Let me just get rid of that. Get the terminal back. Sad that didn't work. OK. The thing about that was it was sort of a diversion from my original plan. I want to hear files. And while waves worked, even the most hardened glitch-core music fan probably wouldn't enjoy listening to them for more than less than a second. Luckily, there's another file format to play around with. MIDI. So MIDI stands for Musical Instrument Digital Interface. And the file format is part of a standard for communicating with actual hardware instruments, like synthesizers and so on. And the part that's interesting to me is that as a file format, instead of storing the actual recorded sound, like a wave, it's more akin to sheet music. And as a format, it's header and data-based, so we can work our magic with it too. So what does a MIDI file look like? It's the header and data that we know and love. The header contains two parts, an identifier that says I'm a MIDI file, and it explains some details about what type of MIDI file am I, and things like time signatures. And then there's a track header that explains the size of the track data to come. The track data, however, it's not like WAV. It's not just smoosh a source file under here and we're done. And it's not like bitmap, where we have to interpret and interleave some padding. It's more structured. It's actually made up of a stream of MIDI events. So a MIDI event is structured. What does it look like? It's made up of time and data. Delta time. This says when the event should occur. It's known as delta time because it's the time since the previous event. So rather than a fixed at this point in the song value, it can be between 1 and 4 bytes. The event data says what the event actually is and can also be broken into 2 parts. We have the type. There's a list of event types. Play a note, set the tempo, do something with the hardware. This is always 1 byte. And then the data contains extra data depending on the event. So playing a note needs data on which note. It's 1 or 2 bytes depending on the type. Let's look at those 3 parts in some more detail. So delta time's interesting. It's stored as a variable length value of between 1 and 4 bytes. It's a space-saving technique. A piece of music could have, I don't know, like 200 notes in it. If you're always storing 4 bytes for the information, that would be 800 bytes. That's ostentatious. For most notes, you probably don't need a 4-byte value to say, play this note really soon after the last note. So if you could store that value in a 1-byte number, you'd save like 600 bytes. That's amazing. How this is implemented is that a single byte is split into 2 parts. You have 7 bits used to store the value, and the remaining 1 bit is used to say if the next byte contains more data for the value or not. 0 means no more data, you've got all the information you need. 1 means read the next byte and find out. Values less than 128 can be stored in 1 byte. Values more than 128 are stored in multiple bytes. In theory, this allows for infinitely large values, as we can keep setting the more bit to 1. In practice, the MIDI spec says 4 bytes is the maximum. This gives us 28 bits in which to store a value, allowing us to store values from 0 to like 268 million. This should be enough for even the longest of long songs. So here's a quick worked example. Where's my mouse pointer? Where's my mouse pointer? Oh, here it is. So a value like 127. It's encoded in bits in 1 byte as a 0 followed by 7 ones. To encode in VLQ, variable length quantity, it's the same. But that first 0 isn't a padding 0 that we don't care about. It's a status bit saying, this value is complete. You don't need to read another byte. A value like 128 is encoded in bits as 1 byte followed by 7 zeros. To encode in VLQ, we need 2 bytes. The first byte is a 1 followed by 6 zeros, then a 1. That first 1 means read another byte. That other byte is 8 zeros, the first 0 of which is the status bit saying this value is complete and you don't need to read more data. So how does that turn back into a value of 128? Well, we can drop the 2 status bits. They're uninteresting. That gives us 6 zeros, a 1, 7 zeros. And those leading 6 zeros are uninteresting to us as well. And that gives us 8 bits, a 1 followed by 7 zeros. And where have we seen that before? Oh, yeah. It's the standard bit encoding of 128. So that's variable length quantity encoding. You may recognize this kind of encoding if you've ever dealt with UTF-8. It is also a variable length encoding thing about how a character can be stored as 1, 2, 3, or 4 bytes. Not this exact encoding, but those MIDI spec designers were onto something. So, event types. This is stored in a single byte, but we only have 7 bits to store the type value because the first bit must be a 1. There are lots of event types, which can be broken into 4 categories. MIDI things that I do understand but don't care about, like lyrics or copyright information. MIDI things I don't understand, like ports and resetting. Music things I don't understand, like tempo or pitch bending. Or music things I do understand and care about. There are exactly 2 of these. Turn this note on, turn this note off. It is 1, 0, 0, 0, 4 extra bits for turn this note on. Turn this note off, or 1, 0, 0, 1, 4 extra bits for turn this note on. The remaining 4 bits of the type contain the channel number in which to play this note, or stop it. MIDI has 16 channels, and a value between 0 and 15 fits in a 4-bit number. So that's convenient. A channel is kind of like an instrument. It's not really, but for our purposes, we can think of it like that. If we think about the event data, it's also stored in a single byte. And we also only have 7 bits to store the type value because the first bit must be a 0. Yes, this means we can easily tell the difference between a type byte and a data byte, which is probably useful for reading files and bailing immediately on corrupt data. Our note events both take 2 bytes of data, one for the key and one for the velocity. Key is literally which key, note to play. For example, middle C, a popular note, I believe, is note number 60. Which is not quite the middle between 0 and 127, but whatever, music nerds. Velocity is how hard the note is played, sometimes known as attack. Think of it like a numerical value for how soft or hard you press the key on a piano, or took your hands off the key on the piano. Other events take different data that mean different things, but all stored in 1 or 2 bytes. So if we put it all together, what do we need to store one of our note on or note off events? Well, we need a delta time, a type, on or off, a key, and velocity. And that looks like this. A byte that starts 0, a byte that starts 1, 0, 0, and then 2 bytes that start 0. Or, because delta time can be 2 bytes, it could be a 1 byte, a 0 byte, a 100 byte, and 2 0 bytes. Or 3, or 4. There's no 5 because delta time is 1 to 4 bytes. Hopefully, you can kind of see the problem that we're getting here. It's very unlikely that our source data file is going to have its bytes arranged so that the first bits magically adhere to this structure. So we can use our source data to fill in the orange parts of this diagram, and we can statically add the blue parts. Our solution is to deal with the bits within the source file, not the bytes. We need 27 bits of data from the source file to make one MIDI event. 8 bits to extract the delta time using variable length encoding. This will be turned into either 1 or 2 bytes. I could use 28 bits, as that's the maximum allowed in a 4-byte value. But it might also mean pausing for hours between notes. That won't be fun to listen to. I could use 7 bits, so it always fits into 1 byte, but I didn't learn about VLQ not to use it. So 8 bits seems like an arbitrary but good choice. And then we need 1 bit to decide if it's on or off, 4 bits to say which channel, 7 bits for the key, 7 bits for how hard, fast, soft the note is played. This way, we can use all the data from our source file and be sure that it's going to be arranged correctly for making valid MIDI data. And here's the code to do just that. First, we read 27 bytes from the source file, and we pad it with zeros if there aren't 27 bytes available, like end of the file. Why 27 bytes? Murray, you said we needed 27 bits. Well, the problem is file reading APIs are byte scale, not bit scale. 27 bytes is 216 bits. Turns out there's no smaller common factor of 27, the number of bits we want per event, and 8, the smallest number of bits we can read at a time. So we read 27 bytes, and that lets us create 8 MIDI events using 27 bits at a time. I told you earlier I didn't like messing with factoring. We turn those bytes into a string of their binary representation using sprintf. The %08b format string says, turn this number into a zero-padded binary number of 8 characters long. We use sprintf because although we can get binary representation with 2s passing in the base, 2, it won't give us the 0 padding at the front, so it won't be 8 characters long, and we need all of those bits. So then we do that. We join them all together as one long 216 character string of ones and zeros, turn that into an array. Then we can loop 8 times through it to pull out the chunks of 27 bits as we outlined before. 8 for the delta time, 1 for the on or off, 4 for the channel, 7 for the key, 7 for the velocity. And then we turn all those bits into the valid bytes we need with VLQ encoding for the time and the static 100s and zeros at the front of the event type and data bytes. The 2i with a 2 is the inverse of the 2s with a 2. It says take this string, interpret it as a binary number, and turn it into a real number? Binary numbers are real. What are you talking about, Murray? We put all of these numbers into an array. And, oh, it's you again, pack. Didn't I say we were done? Anyway, then we pack the whole array as a 1-byte character data, and then we can write that to our file. So now we have unsophisticated but valid MIDI data generated from arbitrary file data. Let's do a demo. Hope this one goes better. Right. Let's clear the screen. So, you know the routine by now. We have an object from Stegosaurus called midriffs this time. Make from the README. And we pass it to the helper function. Now I'm opening this in an app called MIDI Trail that will let me play the MIDI file, but will also show it as a keyboard traveling along a road of notes in space. Because why not? So let's listen to this, the orchestral score of my README. That's pretty fun. That's pretty fun, right? Bit short. I know what you all want. You want Ruby, the orchestral score. So, I hope you are ready for this. So it takes a while because it's not very efficient. All of that bit and byte stuff, turning them into strings and arrays, takes a while. Okay. That's quite a lot longer. Let's see, we can pan around in here, can we? Where's the keyboard? No, not even. Yeah, that's quite the space road of notes. Shall we listen to it? Yes. I assume we might want this for some like parties later. It's pretty good. I mean, it goes on for like an hour. So, I get it. You're probably thinking, why? So let's start with the easy answer. Why Ruby? We don't normally do this kind of thing in a language like Ruby. Bit and byte manipulation is pretty unwieldy. Shouldn't you be using C? Probably, but Ruby's the language I know best. And I was able to get really fast feedback using Ruby. Didn't stop me breaking it this morning, apparently. But, and that feels important to me when I'm playing about with these kinds of toys and silly ideas. And that's really my point here. Pick a tool you know and are comfortable with in order to learn something new. If, like me, you're learning all about bit and byte manipulation and file formats, best not also to be learning a new programming language at the same time. Of course, the flip side to that, if you are learning a new programming language, solve a problem that you've already solved and learn how to do it in the new programming language. And I'll let you into a little secret. That's exactly what I did with this code. The first version of this WAV file generator I wrote in 2004 when I was a Python programmer. In 2007, I became a Ruby programmer, and I decided to port my little thing over to Ruby to try and learn some idioms. It's a good job we glided over the bitmap generator, because I didn't learn very many Ruby idioms when I did it. But yeah. So more existentially, why this? Why this actual thing? It is, let's face it, a pointless little toy, and why have I eaten 44 minutes right now of your life telling you about it? I guess I made it because I was curious, and I thought it would be fun. We don't often get to combine those two traits at work, and that's what I want to encourage by sharing my story. Day-to-day work can be boring, samey. A friend boiled down a lot of what we do to putting strings in a database and taking strings out of a database. And I'm not saying work can't be exciting or challenging or mentally stimulating. It often is. But an important part of a project like this, for me, is the freedom and fun of it all. I'm not making trade-offs about user value and tech debt. I'm not following a roadmap or caring about best practices. I'm just exploring something that's interesting to me and making choices of what to build based on the whim of it. Maybe you're lucky, and the itches you want to scratch are exactly the ones you get to scratch at work. But programming computers is amazing. We can make them do anything with just a few lines of letters, numbers, and too much punctuation. I refuse to believe that you have nothing outside the limited scope of your job that you'd want to make a computer do. I encourage you to embrace that and go and explore some idea that's fun to you. Now, I am categorically not saying, have passion for coding, fill your evenings and weekends with coding. You can do this in your 9 to 5. Think about how you could embrace curiosity and fun in your day-to-day work. What are the opportunities to follow your whims? Look for those or make them up yourself. I shared the RubyConf magic numbers gem not just to shoehorn a work reference in to justify them paying for the trip. Thank you, Cleo. But because it was built by a colleague who wanted to play with RubyConf's AST stuff and managed to fit that into a day-to-day work in a way that would be useful to the rest of us. So maybe you'll learn something useful for work. I learned about space-saving encoding techniques and bit and byte manipulation, which could come in handy if I ever do embedded systems work. Maybe your side projects can spin out into a livelihood. I will happily DJ your wedding with a custom orchestral score made from your personal data. Maybe your side projects will even be useful at work, like a new RubyConf gem to encourage best practices. But those shouldn't be the only reason to do something. This isn't about work, it's about play. All the code lives here if you want to play with it. I'll try and fix it so that it will work. It won't hold up to a critical reading. Every time I come back to it, I find more bugs and put more in, apparently. I said it might be a steganography tool. It's not, because I wasn't interested in writing the reconstruction routines that bitmap and MIDI forced me to do, because this was for fun, and that didn't interest me. Thanks for listening. Bye.